In this video, we will look at some of the elements that make up a basic audio system, starting with loudspeakers. There are a variety of loudspeakers for multiple markets, including installed, cinema, live and touring, and let's not forget recording and broadcast. Within each of these product lines are different types of speaker families: ceiling, in-wall, surface mount, landscape, pendant, and column. The list goes on. At this point, you might be wondering, why on earth are there so many? The answer is simple. JBL has respect for their global audience and understands that each customer is unique. Think of it this way. A shirt that looks good on you may look terrible on someone else. Much like that, a speaker system that sounds and looks good in one place may have the opposite effect in another. But what is a loudspeaker? In basic terms, a loudspeaker is a device that converts electricity into sound waves. We've spent some time already focusing on a couple tools to help us determine how to select a ceiling speaker for a given application and laying out multiple speakers to achieve a desired SPL, intelligibility, and clarity. But what other factors should we consider with respect to loudspeakers? First, let's consider some important specs. Loudspeakers have multiple power ratings: continuous power, or how much power a loudspeaker can handle over an extended period of time; program power, which is normally twice the amount of continuous power and can be used as a guideline for amplifier needs. Lastly, we have peak power, indicating how much power the loudspeaker can handle in short bursts. There are other specifications that one should take into consideration, such as sensitivity, or how efficiently the speaker can convert amplifier power into sound. This spec is generally provided in decibels, and the higher the rating, the more efficiently the speaker will work. Also, nominal impedance. We briefly touched on this in the CSC section. With respect to loudspeakers, impedance is the resistance to power, or you could think of it as obstructing the flow of power. If you're still having trouble with this idea, think of water flowing freely through a garden hose. Now use both hands to put a kink in that hose. Less water is now flowing through because you applied resistance to the hose. Regarding impedance, loudspeakers can fall into one of two categories: low impedance and high impedance. These can be denoted as low Z and high Z respectively. There are pros and cons to both, but each can fulfill the demanding requirements we find in the industry today. Low impedance loudspeakers are rated anywhere from 2 to 16 ohms and most commonly found with a 4 or 8 ohm rating. High impedance loudspeakers are the same as your normal low impedance loudspeaker, but they instead have a transformer on their input. We'll talk more about these in just a moment. Why all this talk about impedance and speakers being low or high? Okay, so the majority of our corporate applications are going to require more than one loudspeaker to provide adequate coverage, intelligibility, and clarity. We'll also want to take advantage of the amplifiers and wire multiple loudspeakers to a single channel in order to provide accordingly for the application. There are two ways we can wire multiple speakers to an amp channel: series or parallel. Let's use an amplifier and two speakers to quickly explain the two different methods. With series wiring, the power source, in this case the amplifier, has a positive and negative terminal for providing power to the speakers. The positive terminal of the amp is wired to the positive terminal of speaker A. The negative terminal of speaker A is wired to the positive terminal of speaker B. Then the negative terminal of speaker B is wired to the negative terminal of the amplifier. With parallel wiring, the positive terminal of the amp is connected to both speaker A and B's positive terminals. Likewise, the negative terminal from the amp is connected to the negative terminals of both speaker A and B. When using series wiring, the total impedance presented to an amplifier is the sum of the individual impedances of each speaker. We'll talk more about amps in the next video, but they are designed to accept an impedance load ranging between 4 and 16 ohms. Some can go as low as 2 ohms. So let's take two speakers, each rated with an 8 ohm impedance. When wired in series, we add them both and find we have a 16 ohm load. What if we want to add one more speaker with the same rating? Well, now we've increased the impedance to 24 ohms, and this simply will not work considering most amplifiers cannot handle anything higher than 16 ohms. Alright, so that rules out series wiring, but what about parallel wiring? When implementing parallel wiring of speakers, the total impedance presented to an amplifier is easy to calculate when each speaker has the same impedance. Divide the speaker impedance by the total number of speakers being wired together. Now let's apply this to our two 8 ohm speaker example. And here's what happens when we add a third speaker. Adding a fourth will lower the total impedance to 2 ohms, and a fifth will lower it to 1.6. As we attempt to add more speakers, we are dropping the total impedance lower than what a lot of amplifiers can handle. That in turn causes the amplifier to create more heat internally and could possibly even catch on fire. Thankfully, many amplifiers today have impedance monitoring circuits that will just shut the amp down if it sees too low of a load. You may be wondering if we can use speakers with different impedance values. You can, but we need to go about the calculation a bit differently. What if we have one speaker at 4 ohms, a second at 6 ohms, and lastly a third at 8 ohms? Let's look at how we would do this. First, take each impedance value and place it into the denominator of its own fraction. You algebra wizards will realize you're taking the inverse of each speaker impedance. Next, let's convert each fraction to decimal. This makes summing the inverse speaker impedances much easier. Now let's think back earlier to when distributed system design recommended we use 20 speakers for our training room, but you might remember that the ceiling speaker configurator said we only needed 12. The difference is that CSE uses an edge-to-edge density pattern and does not allow us to adjust the listener height, but in DSD we did select the overlap density while leaving the height at 4 feet. Let's look at the 20 speakers for our training room. Imagining each speaker has an impedance of 8 ohms, the total impedance presented to the amp would be 0.4 ohms. That's just not acceptable, and there must be a better way. Luckily, with high impedance loudspeakers, we can easily accomplish this task. Remember in the CSC video when we brought up a power company distributing power to everyone's home and likened that to amplifiers and speakers? At the time, it was to fill you in on why we were talking about wattage taps. We'll explore that idea some more. We have what are called distributed systems, also commonly known as 70-volt systems in the US, 100-volt systems outside the US, or high impedance systems. We'll call them 70-volt systems from here on, but regardless of the name we use, they each functionally work the same. Two of the key components of a 70-volt system are high impedance loudspeakers and 70-volt amplifiers capable of delivering the power to those speakers. So the amplifier using either an internal or external step-up transformer sends high voltage, low current signal through the speaker cable to the speakers. Each speaker using a step-down transformer transforms the signal to a lower voltage and higher current that the speaker needs. Again, but more simply, transformers are used to change the voltage and current while the power from the amp remains the same. This allows for a lot of loudspeakers to be connected to a single amp channel in parallel. Let's look at some reasons why we might use high impedance over low and vice versa. We can use smaller gauge wires, saving costs on the speaker cable. It's easier to adjust individual speakers up or down without affecting the others. Think of built-in volume control. We can use a large number of speakers on a single amp channel. Amplifier calculations are easy. And lastly, the transformer can protect the loudspeaker. When using low impedance loudspeakers, we can get more SPL from the same type of loudspeaker. Transformers can limit the low frequency performance, so low impedance speakers tend to do better here. Cheap transformers can add distortion, and they can also saturate, causing distortion across the entire frequency spectrum. So coming back to our classroom design, what would the impedance of our 20 speakers be in a 70-volt system? It all depends on what each speaker is tapped at. Both the 8128s and 8138s have a maximum tap setting of 6 watts. If we're using 20 speakers tapped at 6 watts, the total impedance load will be approximately 42 ohms. If all 20 are tapped at 0.75 watts, then the total impedance load will be approximately 333 ohms. Can you see why we sometimes refer to them as high impedance systems? These values were found using Ohm's law. We'll get more into those calculations in the instructor-led class. And what about power draw? Well, 20 speakers at 6 watts each will be 120 watts, while 20 speakers at 0.75 watts will be a small 15 watts total.